favorite topics in those.
No, what you said?
I was gonna go.
I was looking forward to it.
Hey, get up yourself.
I haven't seen you.
Alright, okay, hey, today. Definitely need your textbook, you need your property sheet today. Today, we're gonna I want to do a quick recap, in case you were gone the Thursday, Friday before spring break. We introduced the conjugate rule. We didn't get any homework on it, we just we did it in class, did a few examples, did some different in-class activities to practice it. Today we're going to review it. I'm going to pick out a couple, I have a couple problems to pick out of the book, so I'll give you kind of the options that you guys would like to see. And then from those examples, we are going to get homework today. Homework that I'm going to assign today, I think I picked out 5 problems, just like before. It's going to be due Wednesday, Thursday, time frame this week. I don't care what day you can turn in. If you're going to turn in Thursday, do it during class, not like the end of the day. But Wednesday, Thursday time frame. But again, it's going to be based on this new rule. But the problem is with the rule that you've learned, it requires that you know all the rest of it. You have to know all the rest because if you successfully do the conjugate rule correctly, that turns into a Pythagorean identity, and then the identity you substitute something else in, which is usually one of these, usually, and it all simplifies from there. So that's kind of the idea. So we're going to practice that today. I have about 3 or 4 problems picked out. We're not going to do all 3 or 4, but I'm going to do at least a few where we can get some practice on it. Now, totally forgot today, we're going to have a new seam chart this week at some point. Kind of be moved around. That'll be later this week. Again, reminder, with the NCAA basketball tournament starting up, it doesn't apply right now because there's no games being played right now. But try to stay off your computers today. Some teachers were definitely warned today that they can take your computer if they see NCAA is on. So just can't keep that in mind today.
Your computer? So that what happens when they take your computer and you meet it later in that class? Be like, oh, sorry, you took it.
Sorry, you're out. You're gonna have to sit there and write on paper. So just be off of NCAA. So they've been forewarned. What? All right. Now here's a select few problems that kind of pick from. I'll let you guys pick 1 or 2 of them that we'll go through. So it's 25, 35. 46, 47. All right, so now it doesn't matter which one you guys pick. They're all basically the same type. They're going to use conjugate rule, and that will eventually kind of mold to the others. I'm not sure about 25. I think 25 you can do it different ways. But so is there any particular one that you would like to do?
46.
46. Okay, let's do that. Okay, we'll do 46 here. All right, now with number 46, again, there's multiple ways to do these problems, so I'll just kind of show you that, but here it is. It's cosecant x, so cosecant x minus cotangent x, and this is squared equals fraction, which is 1 minus cosine x, 1 plus cosine x. Okay. All right. Now, again, just like these problems that we've done before, what we're doing here is we're trying to prove the left and right side are the exact same. So that's kind of what we're at. I don't really mind how you want to do this. This type of problem, there's I can think of just different ways, in fact, how to approach this problem. I'll kind of give it up to you. Do you want to do it with factoring, or do you want to do it with the conjugate rule to practice that?
Conjugate.
Okay. That's the way I recommend this problem. The conjugate rule is probably the easiest way to do this problem, other than trying to factor and all that good stuff. All right. So on the right side there, if you notice it, the right side has the fraction. I usually try to work with the more difficult side. The side that has more stuff going on, because there's more to do. Like this side, there's not really much. The one thing you can do is you write the 2 parentheses side by side, because there's 2 of them, and you FOIL it together. We might have to do that here in a minute. We'll see. I don't know if we'll have to. But on that side, really the only thing we can do is the conjugate rule. Just because the bottom the denominator here is a single binomial. There's no squares or anything like that. So right now, I definitely can't see that it's I can't tell that it's a Pythagorean identity as it sits right now. But if I multiply by the conjugate of the bottom is 1 minus cosine. That will hopefully simplify this problem out. Okay, now notice what I'm doing here. X in parentheses. I have to multiply the top and bottom by 1 minus cosine. The reason being why I have to multiply the top and bottom is what happens when you divide these. They equal 1. So I'm actually multiplying by the number 1 on this fraction. So it's really not changing the fraction. It'll change the look of it here in a minute, but the value of it isn't changed. I mean, no, it's not doubled or anything like that. It's multiplied by the number 1. Now the top, I usually recommend on the top that you don't FOIL, like you don't distribute, because usually something cancels. In this particular case, we might have to. We might actually need to FOIL the top, because the reason why is I notice that it's not going to simplify with anything on the bottom. But we'll see that here in a second. We'll see if we need to go further. So on the bottom, let's multiply the bottom first, outer, inner, last. What do we get on the denominator here? When you do first, outer, inner, last. 1. Yeah, minus cosine x plus cosine x, and then minus cosine x squared. And x, and then that's cosine squared x, right? Because when it's cosine times cosine, which is cosine squared. Then the x is behind it. The middle terms actually cancel out, right? That the plus cosine, negative cosine would actually cancel, and you're left with that. That item right there on the bottom is a Pythagorean identity, believe it or not. It is a Pythagorean identity. I'll show you that here in a second why it is. But we'll replace that here in a second. Now the top I have them separated, but I'm actually gonna let's actually multiply these because it doesn't look like it doesn't have any anything that's gonna simplify. Like this is a binomial up here and a binomial, so I'm actually gonna FOIL these together. So what do we get when we actually FOIL first, outer, and last? 1. It's 1 negative cosine x. Negative cosine x, and then I heard positive cosine squared. Alright, now notice, nothing on the top actually cancels out, as you can tell here. So we'll kind of see that in a second. Alright, any questions with what we did here so far? Okay, I hope you wrote this problem down right. That'd be a nightmare if I didn't. Okay, so it looks like the only thing we're going to do here is let's replace the denominator with that Pythagorean identity, which yeah, exactly right. The Pythagorean identity, if you don't know, there's 3 of them that are on your property sheet. This is the first one. This is like the main Pythagorean identity that we have. You can use this or any manipulation of this to replace things in problems. Like on this problem, and I already heard it. If you move this cosine squared to the other side, right, so I move this over and it becomes a negative cosine squared, right? That is what you see on the denominator there. So I can replace this item on the bottom of that denominator with sine squared. This is of equal value because I can manipulate this thing any way. So I'm going to replace that on the bottom of the denominator. So I have cosine squared, or sine squared. X, and on the top I have 1 minus cosines, actually 2 cosine x's plus cosine squared. Okay. Any questions with what we have there so far? Okay. So far so good. I don't really have anything. I don't have any issues with that so far. On the left side now, because it really doesn't look like anything will simplify up here. Because if I try to factor the top apart, it'll just be that. The bottom, I really can't simplify. There's no signs on the top or anything like that. And nothing's being multiplied on the top, so I can't simplify it anyway. So it looks like I'm going to go to the left side and see what I can do to that. I could break the 2 parentheses and FOIL, or distribute, whatever you want to call it, on the top. I think what I'm gonna actually do is I'm actually gonna jump up to this top, because I think this might be the easier route, possibly. By taking this item and replacing items here, like replacing cosecant with what it's equal to in terms of sines and cosines. So what is cosecant the same as?
1 over sine.
Okay, it's 1 over sine, I agree. So it's 1 over sine x. Cotangent. Sine over sine, all right. And then this whole thing is squared. So when I'm looking in that box, I notice that they have the same denominator, so I can actually subtract those together. So I can actually subtract the numerators, and then the denominator doesn't actually move, right? When you actually subtract fractions, the denominator stays the same, as long as it's the same denominator. And then we have the square. Now, how do you square a fraction? You could square the top, square the bottom, or I heard somebody else say, you multiply the fraction times itself, same thing, right? So, in fact, I'll just kind of write this where I'm going to square the top, square the bottom, because that's actually taking the fraction times itself. So, the fraction on the top is 1 minus cosine x, and I'm going to square that item. So that means there's two of them being multiplied together, and sine squared is on the bottom, right, because I squared the bottom. And that is the same thing that you're looking at over there. Because if I didn't actually like FOIL the top, like let's say I didn't distribute the top, right? I would have came out with the same thing, right? That maybe I want to factor this apart, or maybe I want to leave this alone. That this is 1 minus cosine x times 1 minus cosine x. That was what I had up there, and that's just two of them. So if I didn't FOIL that, we could have got to this point. Usually I always say, like, when you do the Pythagorean, or when you do the conjugate rule, I usually, like the rule, I don't know why it always works this way. They just always recommend you never FOIL the top. And I made a mistake of doing it, but they always recommend just don't do it. Something usually works out in the end on every problem. Case in point, I didn't even have to, because it worked out pretty good, as you can tell. But as you can tell, like, these types of problems, they require everything. You have to know how to use a conjugate correctly. You have to know how to replace things with Pythagorean identities, like our manipulation of them. Or, in fact, just replacing things with sines and cosines. Normal rules that we did 2 weeks ago. Okay, now, they're not difficult problems. As you can tell, what was this problem? 2 steps, maybe 3 total? They're not difficult, but the problem is you gotta know the rule that you're looking at. Do you know even how to start the problem? What side to work with? What to do first? Because I didn't have to do that problem that way. I could have, wrote 2 parentheses down and FOILed first, outer, and last, and then replace things with sines and cosines. I think it would have been more difficult, but could have. All right. Questions, comments on what we did there? Okay, now we had other problems on the board. I'll probably do one more of these. I think, what were the other problems? We had 25, 35, we did 46, that was done. And I think I had 47 or something like that. So is there any of those you'd like me to do?
35.
35? Okay, all right, let's do that. This will be probably my last one today. This one by far in the book is the longest problem I saw, like written wise. It's not the most difficult by any means, but it's definitely the longest when you first see it. So let me write this one on the board. Now, if you were here the Thursday, Friday before we let out for spring break, I think we did this in class activity where people tried different problems out in class. I don't know if it was your class, but one of the other classes had 35 as one of their examples. They had to attempt to simplify it or prove that the right and left side were the same. All right, so let's try 35 here. So secant minus cosecant. So secant theta minus cosecant theta all over secant plus cosecant. Secant plus cosecant equals x minus 1 tangent x plus 1. X theta. put a circle through line. Love it. Alright. And again, now this is my personal thing. Like when you're looking at your problem, and you don't like the variable they use, you can change to any variable that you want. Like you don't like theta, or maybe they use like a t, just replace with an x, that's fine.
Do we even need to have variables in there? We just take them out and do
No, you do. You definitely need to. It's correct mathematics to actually put that in. To me, it's the same thing as like in English, forgetting to capitalize the first letter of a sentence. It's just like one of those rules. You just need to do it. It's one of those common sense things. Because you are taking like a trig function of an angle, so you definitely need the representation of the angle that's sitting there. Yeah, good question. A lot of people always. I know a lot of people, like when they get to college, they start leaving those variables off. They try secant minus cosecant, and professors will lose their mind when they see that. So, you've been forewarned on that one. All right, and I know professors at Iowa State, they get so angry when you replace a variable. Like if they have thetas in the problem, and you replace with an x, you like x better. My professors always lose their mind when they see that. They just get mad. I don't understand that. It's just a variable. It doesn't really matter the symbol they use. All right, so everyone understand the setup on this problem. Now, two ways to do this problem. There's two ways. Number one, you could use the conjugate rule, which is the rule we've been kind of learning Thursday, Friday, right? Where you multiply the bottoms by the conjugates. Second way to do this is avoiding the conjugate rule altogether. So if you're not the conjugate person, you could replace them with sines and cosines, and then deal with the complex fraction and how they, do reciprocals and flip things over. It makes no difference how you do it. It's kind of your personal style. That's why I said, like, these rules are very tentative. Like, you can choose any of the rules you like. You just have to be comfortable with the mathematics and how to simplify the left and right side to prove that they are in fact equal if they are. Because that's kind of the idea. They ask you to prove that the right and left side are equal if they are. So it's kind of up to you. Do you guys want to do conjugate rule? Do you want to do like replacing this with sines and cosines? Conjugate. Okay. So on the conjugate rule, let's. It really doesn't matter the side we want to pick. Maybe we'll do. Maybe we'll work with the. Let's work with the right side that has tangent, because I can think of the Pythagorean identity that has that. Then we can work with the left side. I don't know if that will eventually turn into this one right away. Maybe it's only like 2 steps, maybe it'll take more. I don't think I've ever attempted this problem with conjugate rules, so this will be interesting. All right, so the conjugate, what is the conjugate of this right side? Exactly, yeah. So tangent theta minus 1. Right. And the top is tangent theta minus 1. Right? Because you got to multiply the top and bottom by the same item. We're going to FOIL first, outer, and last. In fact, I'm going to try to avoid. I'm going to avoid doing the distribution of the top. I made that mistake last time. I always say not to do it. So the top, I'm going to leave this tangent theta minus 1, and there's actually 2 of them, so it's squared. So I'm not actually going to multiply those together on the top. Maybe, hopefully I won't have to. The bottom, foiling first, outer, inner, last. What does that turn into? Tangent squared minus 1. Yeah, because the middle terms would be negative tangent, positive tangent. Those would cancel out. And then, I don't know why, it just kind of always works that when you do the conjugate rule, that right there is a Pythagorean identity. So if you have your property sheet out, if you don't know where those are at, Pythagorean identities are right here in the middle of that item here. In fact, I don't even know if that is a Pythagorean identity. You'd have to have a negative secant. Ooh. Yeah, and then so right now that's kind of where we sit. So that is not a Pythagorean identity, which is actually kind of goofy. Usually it always kind of works that way. Let's go to the other side. Maybe that left side will turn into the right side if we do this correctly. I've never actually attempted this problem with the conjugate rule, because that's the way the book recommends it, but I've never attempted this problem like this. So the right side, let's do the same thing, conjugate rule. Actually, I'll use a different color, but that's fine. So what's the conjugate over here? Secant squared, or secant plus cosecant? I've never actually.
No, minus.
Ooh, yeah. spoil first after last. The top, I'm not gonna actually multiply that out. Made that mistake earlier, so let's look at this. Cosecant theta, there's two of them. The bottom is, geez, what was that? Secant squared minus cosecant squared. Now, is that a Pythagorean identity? I don't think it is. It's just kind of goofy. Is that a Pythagorean identity? I don't remember having secants and cosecants in the same.
No, it's not.
Ooh, okay.
So,
So, let's see, because we can't drag, you're not allowed to drag things across to the other side. Never make that mistake. Because we don't know that they're right and left side. Maybe they're not equal. Maybe this is one of those rare problems that they're not actually equal. Yeah, we don't have to replace sines and cosines, because I think that might turn into the tangent idea. So, okay, so let's do that. Because right now, I'm not recognizing that these are Pythagorean identities as of this moment. Like that, if that was a +1, then we're in business. I mean, I'd replace that with a Pythagorean identity, but that was not a denominator. So, yeah, let's do this whole sine and cosine deal. Let's see what this does. All right, so over here, I'm gonna leave that side alone. Maybe that's not the way to do it, but I'm gonna leave that side alone. So over here, what is secant the same as? 1 over cosine. 1 over, what is that? Sine. That's squared. All right. The bottom. This is 1 over cosine squared minus 1 over sine squared. Okay. Whew. That's a difficult looking problem now, isn't it? Okay. So we can do we gotta get common denominators on the bottom, because right now this is, I'm gonna leave the top alone. If we need to, we can change that up. I need to get this to look like tangent squared minus a 1. So let's get common denominators here, because I need to actually subtract these together. Yeah, that is not pretty looking. No. So we need to, let's multiply this by sine squared and that one by cosine squared. And let's see if that'll work out. So, ooh, this is getting ugly. See, I've never attempted it with that rule, even though the book wrote
Yeah,
it.
why'd you choose this one?
Oh, sorry.
That's fine.
I don't have the number now, I'm not supposed to do it.
It's fine. So, we'll keep going here. So replacing this cosine squared, oh, but that would just take us right to the beginning. I don't want to do that. Alright, but multiplying this by sine squared, so the denominator here, so 1 over cosine minus 1 over sine squared, all over, so getting common denominators down here, this is sine squared over cosine squared, sine squared, minus, so that's getting this one to have the sine cosine on the bottom. Over here, that's going to be cosine squared over cosine squared, sine squared. So that's multiplying the denominators by whatever they need to get common denominators down there. Geez, that is ugly, other than my penmanship. I can subtract straight across, and hopefully this is going to start turning into that thing, which, God, I don't see how this is working out with the way we started this. Okay, so this is sine squared minus cosine squared all over cosine squared sine squared. Okay. The top is still not a Pythagorean identity because we had to subtract the tops because they have the same denominator, so I could actually subtract the top. The denominator was cosine squared sine squared. That hasn't worked out to be tangent squared minus 1 yet. geez, I don't know if that goes.
All problems take up the entire board, like all that aren't equal.
No, they usually don't. I think the way we chose this problem was probably not the smartest way to do it by the conjugate rule. Even though that's what the book recommends, I would not understand why they would choose that. Because this didn't work out. I wonder if the book typed that in wrong. Like it should have been a plus down there, even though it's not. Huh. Let's keep going. Let's see. I don't know how they're thinking about attempting this problem, other than actually foiling the top, first, outer, inner, last.
Worth a shot?
Yeah, it's worth a shot. All right, we got to get common denominators here on that, the top. So that would be sine. Should be cosine. And all right, now it's all starting to work out a little bit more. All right, so the top turned out to be sine minus cosine squared all over sine cosine. Whew. Zowie.
We have some similarities, but
How? I'm still trying to figure out how we're gonna get to this guy.
47, I take it up.
No, we can't go back now. We're in too deep now.
Oh.
Using 2D. What if it just doesn't equal?
fancy math
Did you
stuff.
change the tangent to cosine?
We'd have to do the conjugate rule.
What about the top ones?
Does the top equal the bottom?
Double conjugate.
Well, like,
No.
what about the
Or.
It does work out.
I got to here. I zoned out.
No, it's the law of
I zoned out like a blue. Sure.
So we have 2 minutes.
This here. Could you change the tangent to the cosines and sines?
Change that top. Maybe it'll kind of work out to be the same as the bottom right now.
Yeah.
Let's try that.
Have we ever stumped you before, Warren?
The problem is I've done this problem, but I've never done it by the conjugate rule. So that's why it's.
Well, what's the
Did it
answer?
work out the other way?
Yeah. Well, let's keep going here. Let's try changing this one up here, and maybe it'll actually work out to be the same as that. So tangent up here, so that's sine of a cosine minus 1 squared. Where are we at? We're over here. This is sine squared over cosine squared minus 1. Okay. I see some light at the end of the tunnel here.
Glad you did.
Maybe. Okay.
Is this the problem in the book?
Yeah.
I'm
It's
driving.
35. I didn't know that.
You didn't?
Alright. Now, okay, so the top, we're right there. Let's get the common denominators. Maybe it'll start to looking like this thing. So common denominator here would be like cosine. That'd get those things to look the same. So sine over cosine minus cosine over cosine. This is squared, right? And down here, what is that? Get sine squared minus, what is that? Over cosine squared minus cosine squared over cosine squared. So they're starting to look really close, because that top is starting to look like this.
But are they really?
They are. They are certain. Okay. Oh, okay. Here we go. All right.
They're the same.
All right. So the top. So this is the top when I actually subtract, right? So it's sine theta minus cosine theta over cosine theta, right? Because they have the same denominator, and then you square, right? All right. So that's the top. The bottom here is sine squared minus cosine squared.